How good is the approximation of the cubic root function by the degree 2 Taylor polynomial centered at b is equal to 8? Precisely, we ask this question when x is between 7 and 9. And I think it is very natural that we start our discussion by recalling what the Taylor series is and what the Taylor polynomial is. So for example, this is degree n Taylor polynomial. This is something we already know. And now these are some technicalities, you could say. Usually, and this is something I would like to draw your attention to, usually when we summon this theorem, we usually write it as follows. So we write this as some approximation, and we ignore the remainder term. But this is the time. It's time for us to stop ignoring that remainder term. You know, it always seems like this remainder term is something you don't want to talk about, when in fact it is quite useful. And so if you would like to compute the accuracy, then definitely you want to take the difference between f of x and this absolute value and this series. If you do this, then you get the remainder term. Let's call this remainder term Rn, because it depends on n. And notice that it is a function of x. That is because it takes x as input and it outputs some number. So these are two important notes. For the cubic root function, in principle, you could attempt to give an exact description of Rn of x. So this is something you could try to do. Because in principle, if you want to take the third derivative of this function, it's not that difficult to compute. In fact, we will do it in a moment. And then you have n is equal to 2, so this is quadratic, which we know how to expand. So you expand the quadratic, you group the terms, and you integrate part by part, so term by term. And you get some expression. So this gives you Rn on the nose. Now, why am I simply stating this and not moving forward with it? Well, the reason is because I tried to move forward with it in, I don't know, like 6 recordings ago, and I was unable to obtain the intended outcome. Well, I was, but given the time constraint, I think it was too much. So for that, we would like to summon another piece of machinery that will be very useful for this setup. And the idea is to find some other way to talk about the remainder. Now, without holding you for any longer, this is the proposition. So there's something called Lagrange's remainder form for the remainder term. So this Rn of x we can describe as this polynomial, this n plus first polynomial centered at b, and its coefficient is, well, you divide by n plus 1 factorial, and here it is the n plus first derivative of f at some psi. Now, this is very interesting because this doesn't tell us exactly what a psi is going to be. It just tells us that there is such a psi. It exists. And precisely it exists and lives in this interval that starts from B and ends at X. So this is an existence proposition. It doesn't really constructively give us what any description, in fact, about this psi. It just tells us that there is a psi. And this might seem to be useless, but it is not, and we will see why. So to do so, I will try to proceed in this format. The first thing I'll try to compute is fn plus 1 of x. Well, our n is equal to 2. We are trying to compute the second Taylor polynomial. And so we're looking at the third derivative of x. So the third derivative of the cubic root function. Now I can write this cubic root function as x to the 1 over 3. Then I apply the power rule, so I get the following. Let me apply the power rule again, then I'll get and then I will apply the power rule one more time to obtain minus 5 over 3 and then x to the minus 8 over 3. So that is the derivative. Maybe I'll simplify that. So this gives me 27 and minus 2 times minus 5 is positive 10. So that is equal to 10 over 27 x to the minus 8 over 3. Maybe I'll write this as 1 over x to the 8 over 3. And I'll erase this part, or maybe I'll minimize it. Well, if that is n plus 1 of x, then n plus 1 of psi I think I drew it nicely. It is going to be 10 over 27 of 1 over psi to the 8 over 3. Now, what do we know about psi? We know that it is in the interval starting from b and going all the way to, well, whatever x is going to. Keep in mind that our b, which is the center of the polynomial we're expanding at, is equal to 8. This is given to us here. We are expanding the Taylor polynomial at b is equal to 8. So that's good. Now let me write the format for the expression. We are now looking at the following. N plus 1 is equal to 3. N plus 1 is equal to 3. B is equal to 8. And f3 of psi, maybe I'll write it on the side. It is equal to this expression. Now, we would like to move forward with this, and we want to find some estimate for this. Well, this is not equal to 3, this is equal to 2. because n is equal to 2, n plus 1 is equal to 3. I made a mistake. My apologies. I make lots of mistakes. Yes, so we would like to bound this. And I've not written this out of thin air. This probably has to be used at some point. And it will be used now. So if we want to bound this remainder by a number that's bigger, and we have this psi here, and psi is between x and 8, and let me further write this as well. X is between 7 and 9. This is by construction as well. Then what we can do is we can write the following. I'll write the exact same term, but instead of psi, I will put 7. And the reason this works, first off, is because x is between 7 and 9, so I choose the smallest value for x. That's attainable. And the second reason why this works is because psi is at least 8. Psi is at least 8. Now, if psi is at least 8, then I can bound it by something that's smaller. If I divide by something that's smaller in the denominator, I get something that's bigger. And that's effectively what I've done. So I've divided by something that's smaller than, this psi is greater than 7. And so when I divide by 7, I get something that's, well, strictly greater than the other expression. And then for the second fact, I notice that since x is between 7 and 9, then this expression will be at most, so it's less than or equal to 1. That's really what's going on. In absolute value, it is also less than or equal to 1. Because if you think about it, it's centered at 8. X is between 7 and 9. So the farthest you can go from any of the two is one step. So if this is less than or equal to 1, then this remainder is less than or equal to whatever is on the left times 1. Well, times 1, I don't need to write it down, I hope. And we are almost there, because if I open up my calculator, I've prepared it this time, so you don't have to watch me write every single number. Maybe I'll multiply by 1 if you are a bit skeptic. So this gives us 0.00034. Now, this is less than or equal to 0.0004. Now, this is the only choice that's available in the choices. I think the other choices were 0.004 and 0.04 and 0.4. So it's definitely none of these four. So this is what we can say. So this is a strict inequality. But in principle, this is really what we have. This is how accurate the Taylor polynomial is. And isn't that just amazing? So using only the first derivative and the second derivative, so the degree 2 Taylor polynomial, we were able to approximate the behavior of the function around this interval from 7 to 9 with this much accuracy. It's very, very, very close. Very, very, very tiny. So the remainder is at most, the difference in error is at most this number. Which, I mean, it could be very small for you. I think it is small. but at the same time, it is subjective to whoever uses this. So I think if you're doing numerical analysis, which is the field of obtaining approximations to numbers and computations which we cannot find analytical solutions for, it's a very important field for computers, because in principle, if we have an irrational number, we cannot compute it. We can only approximate it. So it is subjective to each case and each person to decide what approximation is good. For example, the first, I think, 13 digits of pi are enough for NASA to make computations regarding the orbits of the Earth and things like that. I mean, I'm not an astrophysicist or something like that, but this is what I know. And sometimes you need more, sometimes you need less. This is again subjective, but be careful, because if your error is too large and it's larger than how you would like it to be, then this can cause errors, cause big problems. I think there was a story where it was also something related to space, and they were computing some trajectory, and they instead of kilometers, they used I think it was yards or feet. I don't know what the story was, and it caused a huge problem, huge error. That was very interesting at the time. Nevertheless, let us not waste the remainder of this tutorial. So we will end it here.